Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to talk about the Maxwell's equation as well as the electromagnetic waves. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description for the notes within this entire discussion. So let's actually summarize every single law that we have already obtained so far. So we have the integral of E vector, the A vector, or pretty much the sum of all of the flux, is equal to the Q over epsilon 0. So this is the charge enclosed over the permittivity of vacuum. And you also get the flux of the magnetic field to be 0. Another one is the sum of the paths so the sum of the electric field over dl within an entire path will be the same thing as the negative change of the flux. And lastly, we got the path of the magnetic field to be a mu0 I, in which I is the current. So this is the entire equation in which we have already dabbled with, but it seems that we see a certain problem. So let's consider this fact. If we have, let's say, a capacitor like this, and then we would have a magnetic field in here because of the current passing through. But let's ask the question, which surface exactly is the current passing through? It could be this one, it could be this one, or it could even be towards within the capacitor. So there's something that is going on. And so we want to discuss whether what exactly is this relation. So let's do a very simple idea in which if you have this positive terminal and the negative terminal, so this is Q, there will be a change of our voltage. So this will be our negative CV equals to Q. So why did I put a negative? This is just for convention anyways. So if we take the first derivative with respect to time, what we get is the negative C dV over dt equals to the current. Now, there is a fact within this in which we could actually obtain our V to be the negative integral of the E vector dl vector. This is something that we have already obtained before. So we could rewrite this as C d over dt of the integral of E vector dl vector. This equals to our current I. Now, based on our Ampere's law, what we see is that in theory, this surface integral over mu0 should be our current passing through. So this is the same thing as the closed integral of B vector dl vector over mu0 should equal to this other integral. But it doesn't seem to be that easy to solve. So maybe we can do something. So for a parallel plate capacitor, we know the capacitance to be epsilon 0A over D. And this is the d over dt of the integral E vector dl vector. This equals to the closed integral of B vector dl vector over mu0. Now, since the parallel plate would technically have a constant electric field, that means that this integral is pretty much just the magnitude of the E multiplied that by the length L. So what we get here is epsilon 0A over D over dt of E times the distance d. So D is in between these two capacitors. And this should equal to the B vector dl vector over mu 0. And so what we could get is that this closed integral B vector over dl vector would be, so this D and this D can be crossed because the D is constant, but the E is not. So it will later have a dE over dt. And then we could just put the A in because it's also constant. And what we'll get inside will be the d phi E over dt, or the electric field, or the flux of the electric field. Epsilon 0, mu 0. So we obtain something like this. And so we could actually just generalize Ampere's law into a much more general case in which it will work for any kind of system. This would be mu 0I plus epsilon 0 d phi E over dt. Now this brings a certain condition in which we have current as well as this other type of current, in which we will call this as the displacement current. Displacement current. So we got the 4 Maxwell's equation, and this is not really written in the book, but we could transform all of these 4 equations into certain mathematical formulas in which it is much more convenient to use using vector calculus. So I want to introduce a little bit about the vector calculus that we'll be using. So remember about this gradient vector or this nabla? This is what we'll call as the partial over partial x within the I hat direction, plus partial over partial y in the j hat direction, plus partial over partial z in the k hat direction. Now this entire thing here was used when we tried to describe about the voltage, in which the negative gradient of the voltage is what we get as the electric field. So since this is also vector, it would also make sense if we actually multiply this not to a scalar, but with a vector. And so there are 2 other types of these operations using the nabla operator. So the first one is by taking the dot product. And taking this dot product here will result something which you call as the divergence of E vector. And for the curl, so also with the cross product, what you will get is the curl of the E vector. Now, what is the exact relation between divergence, curl, and all of these looped integrals? Well, it turns out that if you already take vector calculus, or maybe I will later discuss it more within foundational mathematics, what you would get is that there is a relation between triple integral and double integrals by transforming it into a divergence or curl depending on the usage. But in here I will just introduce it in a very shallow manner. So let's actually rewrite all of the Maxwell's equation first. So the fact is that you could actually rewrite a you could write a double integral like this of E vector dA vector into a triple integral by multiplying it with the divergence of the E vector dV. And so if you do this for the first Maxwell's equation, or the Gauss's law for electric field, you could just get rid of the dV as well as the integral. What you get is the divergence of the E vector should be equal to the charge density, or sometimes it is written as rho, over epsilon 0. So this is the first thing that you could get. Same idea with the magnetic field. If you do the same thing, what you would get is this would equal to 0. And so we could also transform this looped integral for a loop of E vector the L vector is by, I believe it is the Green's theorem, and the previous one was the Stokes theorem, is that you could transform this into a double integral with the curl of the E vector dot the dA vector. So it becomes into a surface integral. And so later with the surface integral, you could just cross out the entire fluxes to obtain the following. The curl of the E vector will turn out to be the negative partial B vector over partial t. And the same thing is true for your B vector, which is going to be the J vector over, no, sorry, it will be mu 0, multiply that by the J vector, or the current density, plus epsilon 0, the partial E vector over partial t. So with this for Maxwell's law, we could try to visualize this law in a vacuum in which there is no particles, there's no charge densities, there's no current, and see what will happen to our equations. So you could do this for the integral form or maybe the differential form, in which I will do in this video. So if we assume the charge density to be 0 and also our current to also be 0, what you would get is the partial, so the divergence as well as the, so the divergence of both the electric field and the magnetic field will be 0. And the curl of the electric field will be negative partial B vector over partial t, and the curl of the magnetic field will be the partial, it's mu 0 epsilon 0 partial E vector over partial t. Now this is where the trick within vector calculus comes in. So a relation within vector calculus that we could use is the partial derivative cross the E vector, or A vector technically, because this is in general. What you would get here is this will be the same thing as taking the gradient of the divergence, subtract that by the Laplacian of the A vector. And so if you try to solve this entire thing and just trying to plugging it into one of the E or the B, so in here I'll just put in the E and see what will happen. So what we'll get on the left hand side will be the nabla cross negative partial over partial t of B vector is equal to the gradient of the divergence of A, which turns out to be 0, so that means this is also 0. Subtract this by the Laplacian of the E vector. And then from here, what we could see is that there is this negative partial over partial t of the B vector. And we'll just assume the position as well as the time are independent, so we won't really deal much with the relativity. So what we will get in here would be the negative partial over partial t. So inside there is the curl of the B vector, which turns out that we have already known this. Mu 0 epsilon 0 partial E vector over partial t. And this equals to the Laplacian of the E vector. So what we get in here is mu 0 epsilon 0 partial squared over partial t squared of E vector equals to the Laplacian of the E vector. Now, this might not seem to be quite interesting, but we have already discussed about waves, in which there is this in which we have this relation. So when we deal with waves, something that we obtained was the partial squared over partial t squared of, let's say, y is equal to the partial squared y over the partial x squared. And what we multiply in here is the speed of the wave. And this has the same form. So what we see here is that the v squared turns out to be 1 over mu 0 epsilon 0, or the speed of this electromagnetic wave is 1 over the square root of mu 0 epsilon 0. So this is the speed. And if you plug in the values, this is about 3.00 times 10 to the power of 8 meters per second. Now, this value is actually exactly the speed of light. So people are starting to think that if that light is pretty much just a electromagnetic wave, and that's why we could actually observe light even though there is no particles. So this is where the idea of light is not really a particle, but instead as an electromagnetic wave. But when you start to deal with quantum mechanics, what you will observe is that light is also a particle, in which it has particle-like effects as well. So we will later discuss about this much more further when we start to deal with quantum physics. But in here, I want you to accept that light is just an electromagnetic wave. So let's just try to solve one type of solution for this electromagnetic wave. Since we have determined that this is a wave, we could just guess that one of the functions would be the E vector equals to EP sine kx minus omega t in the j hat direction. So what this means is that you would have a plane wave that is propagating in the x direction with its electric field pointing within the y direction. So this is a transverse wave. So let's just try to put it into our equations, and if you try to solve the entire Maxwell's equation, it should all make sense. I mean, if you try to put the divergence, it's obviously going to be 0 because there's no y component. And then for the magnetic field, we'll later try to solve for that. Well, actually, we could just solve it right now. So, what we observe is that we could actually get we'll just do the curl of the E vector should equal to the partial over partial t, negative partial over partial t of B vector. And let's solve for the B vector. So taking this cross product, what we'll have is that there is this ijk, right? And there's the partial over partial x, partial over partial y, partial over partial z, and then there's nothing here, 0, 0, and then this is where our EP sine kx minus omega t is located. So the result will be in the k direction, and we just need to take the derivative of this guy in terms of x, so that's EP cosine kx minus omega t, multiply that by the k. So this should equal to the negative partial over partial t B vector. So if we take the integral in terms of t, what we would get is this to be equal to k over omega EP sine kx minus omega t of the k vector. And this is our B vector. So what we'll obtain is this sine kx minus omega t. So what we could observe here is that the peak of our magnetic field is k over omega EP. Or this is the speed of light times the magnetic field peak equals to the electric field peak. So this is one of the conditions in which if you have this electric field, it must have this certain magnetic field. But their phases are still the same. But this is not true if you're dealing with standing waves. It has another property in which you could use the Maxwell's equation to solve what's the magnetic field component. So I want to introduce a little bit about the waves idea. Remember that omega over k should be our velocity, but also the lambda multiplied that by f will also result in our velocity. So make sure you remember the conversions within waves as well. Now, there are certain properties of light or electromagnetic waves. The first is that it has a phase it has a orientation, and it also has polarization. So what does this all mean? So phase is in which we write the we write the waves in terms of kx minus omega t plus phi, in which the phi here is our phase. So it could be in phase, it could be out of phase, depending on the periodic motion. Orientation determines about where does this electromagnetic wave going to? Is it going in one direction? Is it going to the other direction? So this is similar to our V. And it turns out that we could actually determine the propagation of the wave through using the electric field and the magnetic field. So if we try to analyze this, what we observe is that this E vector cross B vector is the direction. So you could prove this using vector calculus as well, but in here I'll just present it as it is. It turns out that this E vector cross B vector is pointing in the same direction as the velocity of the wave. And lastly is the polarization. So what does polarization really mean is that remember that electromagnetic waves are pretty much longitudinal. This means that the electric field is perpendicular to the orientation of the wave, or the propagation of the wave. And this is what you call as the polarization. And why is this important? Is that this is due to the fact that if you actually put, let's say, a polarizer, and then there's a wave going through, what will happen is that it will try to diminish the wave so that it is traveling within the correct polarization. And so let's just do an example of this type of question and see what kind of property does it have. So let's say our electromagnetic wave is going within this direction, and then we put a polarizer within this direction. So it wants the wave to be traveling within this direction, well, specifically the electric field. So it is positioned at angle theta. And let's see what's the magnitude of our wave. So our E vector will be the original peak, multiply that by the cosine of theta. And that's pretty much it. But later I will discuss about the power of the wave. But I will just present this straight on, is that if you take the E vector cross B vector, which is a relation of the intensity, so this is something that's proportional to the intensity, what you would get is, this will be from our peaks first. This will be EP cosine theta. That's from our electric field, and then cross the B vector, which its relation with the electric field should be E equals to C. No, sorry, the B equals to E over C. So it's EP cosine theta over C. So this would turn out to be EP squared over, oh sorry, let's don't do that, but we'll just write this as BP. So pretty much the wave itself is, oh no, sorry, actually we could just write this like this. So we get EP cosine theta and BP cosine theta. And this EP times BP is pretty much the EP vector, the E vector cross B vector of the incident wave, cosine squared theta. And so if we use the certain proportionality constant to turn it into actual intensity, what we would get is that this S would equal to the original S times the cosine squared theta. And this is what we call as the law of Malus, in which you could determine what's the intensity depending on the polarization. So after I have already discussed a lot about these properties, it is fundamental to note that this this electromagnetic wave determines almost every single wave that we use within our daily lives. So what we could actually see right now is something which we call as the visible light. So visible light has a spectrum of about 400 nanometers to 700 nanometers, depending on the textbook. And then what you would have is that before, and so values above 700 nanometers, what you would get is some long waves, something like radio, microwave, as well as infrared. And then for values lower than 400 nanometer is that there are UV, there are X-rays, and there are also gamma rays. So now, after you have already understand about what exactly light is, so the question is, how do we produce this electromagnetic wave? So the way that you would actually generate an electromagnetic wave is that first, you need to have a moving charge in order to create a magnetic field. But what you want is not really a constant magnetic field, otherwise you don't have any electric field. Instead, you want to have a changing magnetic field. That's why you need a changing velocity. And so what this changing velocity here is pretty much what you call as acceleration. And so this is why sometimes you would see antennas in which it has this like long stick. So it goes something like this, right? And so you would actually give it a AC current. So if you plug this into AC current, what you would have is a propagating wave of currents in which it will be forced to go in one direction and then the other direction. And this will in turn create a electromagnetic wave. And another idea of this is by actually spinning a electron. So just to create a localized source of energy. Sorry, of electromagnetic wave. So pretty much like atoms, in theory they should emit a electromagnetic wave. But it turns out that when you go into the quantum world, it is observed that these electrons doesn't really produce light. So the model of atoms isn't really about a proton as well as an electron whizzing around. But it is some other model, in which we'll later discuss much more further when we are starting to deal with quantum physics or maybe even atomic physics. So I mentioned a little bit about the energy within a wave system, but I didn't fully discuss about it. Maybe even the intensity. So this is where I will try to discuss much more about the energy. So remember from last time, in which we figured out what's the energy density for the electric field as well as the magnetic field, or the electric energy and the magnetic energy. So the value is half times epsilon 0 E squared, and then for magnetic energy it's B squared over mu 0. And this is just the density, so we would just try to multiply this by a small volume. Let's just do it like that. A times dx. So with this, we could try to simplify some stuff up. So what we could actually observe here, so first what we'll do is that we'll just assume that the electric field and the magnetic field within a certain point doesn't truly change because it's a very small time scale. So what we'll do is that we'll just do this over time. And this is what we also know as power. So the power is the du over dt, and we'll just assume that everything like the energy density is pretty much constant. So what you would have on the outside would be d8 times dx over dt, which is the speed. So I'll just denote this to be the speed of light, multiply that by the area. Now we could make this in a much more general sense. let's just actually make this into P over A. So that's power over area. And this is what we will call as the intensity S. So this value will be C over 2. Actually, we'll just put the mu 0 outside, and we'll just put the C inside. What you would get is C mu 0 epsilon 0 E squared plus B squared. So we could now try to substitute something. Maybe what we know is that E equals to CB. So we could just substitute one of the E into a B and then one of the B into an E. So they would both have the same variable at least. So if we combine it, it will become 1 over 2 mu 0 C mu 0 E0 C EB plus B times E over C. So we could actually try to remove a C towards the outside and also the EB. So first of all, what we see here is that there's a C squared mu 0 E0. So this is just a constant. Sorry. So in here there should be another C here. So it turns out that the C and the C will cancel each other out, and then C squared is 1 over mu 0 epsilon 0. So this means this entire thing goes to 1. What we'll get is that this EB over mu 0 is our intensity, or this is what we could also call as our Poynting vector magnitude. So the Poynting vector tells you where the wave is pointing at, as well as its energy density, pretty much. Sorry, the power density. So it is defined to be the E vector cross B vector, which is the direction of the wave, over mu 0. And so for a sinusoidal electromagnetic wave, on average, so you could use the same probability that I have already taught you on the last video. This would be pretty much just the E peak over B peak over 2 mu 0. So this is the average intensity of the electromagnetic wave. But this could also be converted into other parameters. For example, E equals to CB. That means that it's the same thing as the peak squared over 2C mu 0. Or it's the same thing as the magnetic field peak squared times C over 2 mu 0. It's the same idea. So what we have determined here, this E cross B over mu 0 is the power over area. But let's think about another specific kind in which we could actually determine what the power is. Or maybe much more specifically, if we know the intensity within a certain range, we could determine what's the power within a certain point. So the idea is that if we have a zero-dimensional light source which propagates its energy towards every single direction, we could determine what is the intensity at a certain point, since it is symmetric within orientation. So if we draw a sphere in which this, let's say the source is emitting a impulse, so it is going to be using its power. So based on the law of thermodynamics, what we saw is that the energy shouldn't dissipate unless, obviously, if it turns into thermal energy, and which we will just not assume that to be the case. So all of the energy will turn out to be the electromagnetic energy. So the one on the outside here should also have the same power, but it is distributed over its area. So it's the power over the area of 4 pi r squared. So r is our distance. This is our S, or our intensity at that particular point. So intensity is just pretty much the power over area. So what we have already discussed is the energy of a electromagnetic wave. So maybe you could also think about, what about the power? Or, no, sorry, not the power, but instead something like the pressure or like the momentum. So we have already talked about the energy or the power of this electromagnetic wave. So now we can start to ask about the momentum. So the way that we'll actually try to get the momentum is a little bit tedious, but we'll just get that through. So let's get this going first by understanding what energy is. Energy is the force multiplied by the displacement. Now if you do this over time, what you would get, the du over dt in here, is what we call as the power. And this will be the force as long as the force is constant. Multiply this by the velocity. So in here, in which if we already have the power, this would equal to the force, multiply that by the speed of light. Now we obtain what is the force done by an electromagnetic wave. So if we try to understand this a little bit further, F equals to the dp over dt. This means that we could substitute this thing in again. So power would equal to dp over dt, where this p here is momentum, multiply this by the c, and we'll integrate both sides by t. So this will be the u again, which will equal to p times c. So momentum is u over c, in which the p in here stands for momentum. So this is a relation in which you will later normally deal with when we're dealing with relativity. So now, after we have fully understand about this, we can go much more deeper and talk about what about the momentum over area, or pretty much the force over area, pretty much. Since we have already figured out what the force is, which is the power over the speed of light. So if we divide this entire thing by A, what you would get is this radiation pressure. This radiation pressure would be the pressure over A, which is the intensity over your speed of light. So this is what we will call as radiation pressure. And this is very useful when you're dealing with laser physics, in which you could suspend a material just by hitting light with it. It's like as if you have a small particle in which it has a certain mass and a weight, and then you shoot it with light. So you could just put in some EM waves, and because it has a momentum, it will be suspended in the air. So this is all about Maxwell's equation as well as the electromagnetic wave, in which we have started from the Maxwell's equation of electromagnetism, and we have moved forward into this ground place of optics as well as a little bit of laser physics. So going forward, what we'll be doing is that we'll study the properties of light and how it is interacting between different materials, different spaces, and much more. So thank you very much for watching, and please consider liking and subscribing, and also please share this to your friends who really needs to understand physics in a much more better understanding. So thank you very much, and I will see you on the next video.